In this video, I'm going to discuss the proof of the theorem limit x approaches to 0 sine x over x. This is equal to 1. The theorem right here says two things. First, the limit as x approaches to 0 sine x over x exists. In other words, this means the limit x approaches to 0 from the left hand side sine x over x is equal to the limit as x approaches to 0 from the right hand side sine x over x. The second thing is that the limit is equal to 1. That means each of the left hand limit and the right hand limit is equal to 1. So when we do the proof, we have to show both cases. That means basically I have to show that the left hand limit x approaches to 0 from the left hand side sine x over x is equal to 1, and also I need to show that the right hand limit as x approaches to 0 from the right hand side sine x over x is equal to 1. When we prove these two things, then we can conclude quite easily that limit x approaches to 0 sine x over x is equal to 1. Alright, so for the proof, I'm going to use a geometric construction. For the geometric construction, I'm going to need a circle. And then I need to locate the center. Let's say the center is somewhere here. Let's assume that the radius of this circle is equal to r. And then I need to develop this construction some more. I'm going to need a sector inside this circle. So let me go ahead and draw a sector. Alright, here we have a sector. Now I'm going to label these endpoints. I'm going to label the center as O, the endpoints of the sector as A and B. I need to do some further geometric constructions. First, I need to draw a perpendicular from A to OB. Let me label the base of that perpendicular as C, and then I need to connect the points A and B. Now I have to do two more constructions. I need to extend the line OB, and then I need to draw a tangent to the circle at A. Now the construction is complete. Let me go ahead and erase this little line segment. Let me label the point of intersection between extended OB and the tangent that was drawn to the circle through point A as point D. Now I have a question for you. What should be the size of angle OAD? Angle OAD should be 90 degrees. That's because AD was a tangent drawn to the circle at point A, and OA is the radius. We know that always the radius is perpendicular to the tangent. In addition to that, AC was drawn as a perpendicular to the line OB. Therefore, the angle right here should also be 90 degrees. Now I need one more thing. I'm going to label the angle AOB as angle X. Now, can you find the length of AC? And also we are going to need the length of AD. First, see if you can find the length of AC. We know that the radius of this circle is equal to r. That means the line segment OA should have a length of r. Now if I write down an equation for sine x using the triangle OAC, we know that sine x is equal to opposite over hypotenuse. So the opposite is equal to AC, and the hypotenuse OA is equal to r. Therefore, from that I can find AC. From that we have AC being equal to r sine x. We are going to need that. Similarly, can you find AD? If you look at the triangle OAD, we can write an equation for tangent x. Tangent x should be equal to opposite over adjacent. Opposite is AD, adjacent is OA, which is equal to R. Therefore, from that equation we have AD equals R tangent x. We are going to need that as well. Now we are going to pay attention on three geometric shapes that we can see in this construction. First, you are going to look at the triangle OAB, and then you are going to look at the sector OAB, and finally you are going to look at the triangle OAD. Out of those three geometric shapes, which one has the smallest area? The smallest area is for the triangle OAB, and the area of the sector OAB is larger than the area of the triangle OAB. And also, if you look at the area of the triangle OAD, that's going to be the largest. So let me write it down as an inequality. We know that the area of the triangle OAB is the smallest, so let me write it first. The smallest area is for the area of the triangle OAB. Area of the sector is larger than that. Area of the sector OAB is larger than the area of the triangle OAB. And we know that the area of the triangle OAD is the largest. So let me write it down as that. Area of the triangle OAD. So if you pay attention on what I have written, I wrote area of triangle OAB is smaller than or equal to the area of the sector OAB, which is smaller than or equal to the area of the triangle OAD. Well, the equality holds only if that x is so very small. But in this configuration, the equality doesn't make much sense. Alright, now I need you to write down the equations for the areas of these three things. Can you still remember how to write down the area of a triangle? Area of a triangle is equal to 1/2 times base times height. Therefore, we can quite easily write down the area of the triangle OAB. Area of the triangle OAB should be 1/2 times the base OB, which is the radius, therefore write it as times R, times height. Height is AC. We saw that AC is equal to R sine x. That should be smaller than or equal to the area of the sector OAB. Can you still remember how to find the area of a sector? From plane trigonometry, we know that if you have a sector whose radius is equal to r, and if the angle is equal to theta, the area should be equal to 1/2 r squared theta. Now for our geometric construction, the radius is equal to r and the angle is equal to x. Therefore, the area of the sector OAB should be equal to 1/2 r squared x. That should be less than or equal to the area of the triangle OAD. For the triangle OAD also, I need to find the area as 1/2 times base times height. 1/2 as the base, I'm going to use OA. As the height, I'm going to use AD. OA is equal to R times AD. AD was found to be equal to R tangent x. Now we can do some simplifications of this inequality. As you can see, we have 1/2 as a common factor in all three of these pieces. Therefore, I can go ahead and divide out 1/2 from all of these. 1/2 is a positive quantity. Therefore, it will not change the inequality. And in addition to that, you can see each term has r squared as well. The first term has r squared right here, the second term has r squared right here, and the third term has r squared right here. We can divide out that entire inequality from r squared as well. We know r squared is positive. When you divide an inequality by a positive quantity, the inequality stays exactly the same. Therefore, I'm going to go ahead and cancel off r squared as well. Now I'm going to write down the remaining pieces. From that inequality, from this first one, I only have a sine x term. Less than or equal to, from the second one, I only have x. Less than or equal to, from this third one, I only have tangent x. Now what I'm going to do is, I'm going to pay attention on the limit. What we need is limit as x approaches to 0. We cannot talk about limit as x approaches to 0 straight away, but we can talk about the two cases, as limit x approaches to 0 from the right hand side, and also as limit x approaches to 0 from the left hand side. So the first thing I'm going to do is to pay attention on the limit as x approaches to 0 from the right hand side. So let's look at this inequality as limit x approaches to 0 from the right hand side. Let me open some parentheses and write down the inequality as it is. We have sine x being less than or equal to x, which is being less than or equal to tangent x. Let me close parentheses. Now I have a question. Can I go ahead and divide each of the three terms of this inequality by sine x? In order to answer that question, I need to know two things. First thing is sine x equal to 0. If it is equal to 0, we cannot do the division by 0. Therefore, we have to first check that condition. We have limit x approaches to 0. That means x is not equal to 0. X is not equal to 0 means sine x will not be equal to 0. The second condition to be checked is whether the sine x term is positive or negative. Because if it is positive, when you divide everything by sine x, there will be no change happen to the inequality symbol. However, if your sine x is negative, when you divide these pieces by sine x, what should happen to the inequality? The inequality should reverse. Alright, so for this case, is sine x positive or negative? When x approaches to 0 from the right hand side, we know that sine x should be positive because x is slightly more than 0. In that case, sine x should be positive. Therefore, I can freely divide everything in this inequality by sine x. Let me write it that way. Divide by sine x. Then we have limit x approaches to 0 from the right hand side. When I divide this first piece by sine x, it's going to be sine x over sine x, which is equal to 1. The second term in this original inequality is just an x, and it has to be divided by sine x. Therefore, the middle term becomes x over sine x. The last term in the original inequality is a tangent x. When you divide tangent x by sine x, what do you get? We know that tangent x is equal to sine x over cosine x. When that's divided by sine x, we are left with 1 over cosine x. So let me write it that way. 1 over cosine x. Please note that this inequality is written for the case where x is approaching to 0 from the right hand side. Now I'm going to practically evaluate this limit for each of these three cases for this inequality. Or in other words, let me distribute limit x approaches to 0 from the right hand side into each of these three pieces of this complete inequality. When I do that, I have limit x approaches to 0 from the right hand side 1 less than or equal to limit x approaches to 0 from the right hand side x over sine x less than or equal to limit x approaches to 0 from the right hand side 1 over cosine x. Now we can quite easily evaluate these two limits on the two sides. When I evaluate those two limits, there is of course no x term in that first term, therefore it is just 1 less than or equal to limit as x approaches to 0 from the right hand side x over sine x less than or equal to, how do you evaluate this limit? Limit x approaches to 0 from the right hand side 1 over cosine x. We can directly substitute. We know that cosine 0 is equal to 1. Therefore that limit also becomes 1. Now according to this relationship, we can conclude that limit x approaches to 0 from the right hand side x over sine x should be equal to 1, because that middle term is greater than or equal to 1 and it is less than or equal to 1. Because of that reason, we conclude that limit x approaches to 0 from the right hand side x over sine x is equal to 1. Now from that, I can quite easily flip that and write it as limit x approaches to 0 from the right hand side sine x over x is also equal to 1. If I flip this function, I just have to flip the right hand side. So 1 over 1 is also equal to 1. Now I'm going to box this equation and label it as equation number 1. I still have to prove that this equation holds true even for the case where x approaches to 0 from the left hand side. So let me go ahead and work on that. The original inequality that we have is right here. Let me label it as inequality A. The inequality A says sine x is less than or equal to x and it's less than or equal to tangent x. So I'm going to go ahead and copy that inequality one more time. Alright, here's the inequality. Now I need to evaluate the limit as x approaches to 0 from the left hand side. The limit as x approaches to 0 from the left hand side this time of this inequality. Let me open parenthesis, and inside the parenthesis I have sine x less than or equal to x less than or equal to tangent x. Close the parenthesis. Now again I need to ask that question. Can I go ahead and divide everything by sine x? To answer that question, in this case also, I have to look at two things. First, is sine x equal to 0? Sine x is not equal to 0 because limit x approaches to 0 from the left hand side means that x is not equal to 0. Therefore, sine x is also not equal to 0. So the first question answered. The second question is sine x positive or negative? Because if it is negative, I need to flip this inequality symbol. For this limit, we know that x approaches to 0 from the left hand side. X approaches to 0 from the left hand side means x is negative. That means sine x is negative. Now if I need to go ahead and divide everything by sine x, this term and also this term, let me write down what I'm going to do. I'm going to divide by sine x. We still have limit x approaches to 0 from the left hand side within parentheses. That inequality I'm going to divide by sine x. So the first term, sine x divided by sine x is equal to 1. Remember, sine x is negative. Therefore, I'm going to flip this inequality to the other side. greater than or equal to x is going to be divided by sine x. Therefore, the middle term is now going to be equal to x over sine x. Again, this inequality will also be flipped. So it will become greater than or equal to tangent x divided by sine x. Once again, since tangent x is equal to sine x over cosine x, tangent x divided by sine x should be equal to 1 over cosine x. Let me close the parenthesis. Now I'm going to distribute the limit x approaches to 0 from the left hand side into each of these three pieces of the inequality. When I do so, we get limit x approaches to 0 from the left hand side. The first piece is 1 greater than or equal to limit x approaches to 0 from left hand side x over sine x greater than or equal to limit x approaches to 0 from left hand side 1 over cosine x. Now, just like earlier, I'm going to keep this middle term as it is and evaluate the two limits on each side. Then this first term, it has nothing to do with x, therefore it will be just equal to 1 greater than or equal to limit as x approaches to 0 from the left hand side x over sine x, which is the middle term, should be greater than or equal to what should be the value of this limit. As x approaches to 0, 1 over cosine x. We know cosine 0 is equal to 1. Therefore, the direct substitution works, which is equal to 1. Therefore, from this relationship, we can see that this middle term is greater than or equal to 1, and also it is less than or equal to 1. That means we conclude that as limit x approaches to 0 from the left hand side, x over sine x should also be equal to 1. Now, just like earlier, I can flip that and write down that limit x approaches to 0 from the left hand side sine x over x being equal to 1. I need to flip these two inequalities. Let me box that relationship as well and label it as equation number 2. Let's go ahead and revisit equation number 1. In equation number 1, we proved that limit x approaches to 0 from the right hand side sine x over x is equal to 1. Under equation number 2, we proved that as x approaches to 0 from the left hand side sine x over x is equal to 1. Therefore, according to those two results, number 1 and number 2, we conclude that the limit as x approaches to 0 sine x over x exists and it's equal to 1. This is the complete proof of the theorem that limit x approaches to 0 sine x over x is equal to 1. In this video, I'm not planning to discuss any worked examples. However, this is a very important theorem. There are plenty of possible questions that can be generated from this theorem. I will have a separate video explaining a set of selected problems which are direct applications of this theorem. Alright, so I'm going to go ahead and stop the video at this point. Thank you so much.